Hi there and welcome to my video. My name is Raymond Doe and today we'll be taking a look at my Physics 2211 Lab 3 video, Black Hole. Enjoy. So the purpose of this lab is to demonstrate computationally the physics of two-dimensional curving motion by accomplishing two things. We'll first calculate the theoretical mass of a black hole by using a computational code that employs the physics principles of curving motion of an orbiting object. And then we will simulate the motion of a spaceship around the planet and black hole by calculating all necessary gravitational forces and using Newton's second law to predict the motion and velocity of the planet and your spaceship. Some of the key fundamental principles we'll be utilizing in this lab will be Newton's second law, the momentum principle, perpendicular and parallel motion, and universal gravitation. All of these equations you can find on your left side, and we'll even be using some derivations of these equations, such as the velocity update and position update formula. By the end of this video, we'll be able to visually understand the effects of universal gravitation and how the parallel and perpendicular components of an object's force, affecting its speed and direction respectively, are represented while moving in a circular motion. To do this, we'll use the key concepts and principles listed before to generate theoretical orbits of a planet and spaceship around a black hole. In part 1 of this lab, we'll use the properties of parallel and perpendicular motion of net force to determine the mass of our black hole. Establishing initial conditions, our system in this case is of course the black hole, and our surroundings are the star. My foundational information G is simply the gravitational constant. The mass of the star was given to me, and my delta T is calculated as the number of seconds in a day. In the bottom left, you can see how momentum and the derivation of the momentum principle is implemented into my code. And to your right, you can see how I've used the equations of parallel and perpendicular forces to find F net, which I plug into the formula to find the mass of my black hole. This is my resulting figure with my star orbiting the black hole. Displayed here is my net force in full, parallel, and perpendicular component values, but most importantly, we now have the mass of the black hole. Despite the net force along with its perpendicular and parallel components being equivalent to the rate of change in momentum in principle, they can be determined in starkly different ways. While we can determine the rate of change in momentum by simply observing an object's position, velocity, and momentum over a period of time, computing the net force will require us to know the approximate mass of the object, thus making calculations of the net force a bit more difficult. Now for part 2 of this lab, we will once again establish initial conditions. The system in this case will be the spaceship, with the surroundings being the black hole and the planet. Much of our foundational information is the same as it was in part 1, with the inclusion of our black hole mass that was previously found. My ship speed was determined through several trial and error runs, and I used the velocity and position update formulas as seen in the bottom left. To my right is me simply utilizing the formula for universal gravitational force on objects such as the ship and planet, and summing those forces to determine the net force acting on those respective objects. This is my new resulting figure, and as you can see, the planet colored in cyan can successfully orbit the black hole without crashing into the spaceship colored in magenta. When asked what initial velocity would your spaceship need to have in order to enter some kind of orbit around the black hole, my process was still a bit trial and error, but with the help of a derivation of the universal gravitation formula, which yielded the figure to your left and the equations and velocity vector to your right. Possible errors that may be found in this lab can be largely attributed to the trial and error process in which the initial velocities of the ship were determined, meaning that more precise or appropriate values for the velocities could likely be further deduced. Thank you for your attention, and I hope you've enjoyed.